So, if you look at what we have seen till now, we have looked at what is force, what is pressure, and last session we were looking at the pressure exerted by liquids, right? And what are the things we saw? We found that the pressure exerted by liquid is directly proportional to the vertical height of the liquid column. It is directly proportional to the density, which is mass per unit volume of the liquid, and also the pressure is exerted. A pressure at a point in a specific depth in the liquid is exerted in all directions. And what is that law called? Pascal's law. Wonderful, right? So we have seen all these concepts in the last session. Now what we're going to do look at is, now just like when we looked at the consequences of a solid pressure, we looked at various aspects there, right? Similarly, we will actually look at the consequences of air pressure. But before that, I want to do some problems based on liquid pressure, right? So say that we have a tank. We have a tank. I'm just drawing a tank here. Okay. Now this tank has water inside it. Okay, so it has got water inside it, and this is water inside it. Okay, there's water inside it, and the height in which the water is there, this height is this height is 10 meters. Okay, so this 10 meters, so the water, it's a big water tank, and it is inside the water tank there is water which is at the height of 10 meters. Okay, now the area, this is actually a rectangular tank, so the length of the tank is 5 meters, right? And breadth of tank is 4 meters. Okay, now the question is, first is, what is the pressure exerted by water on bottom of the tank? Bottom means, what is the bottom? Bottom surface is this one, right? So this is the bottom. This is the bottom of the tank, right? So what is the pressure exerted by water on the bottom of the tank? First question. And the second question is, what is the force exerted by water on bottom of the tanks? So these are the two questions. Now how do you do this, right? If I want to know the pressure exerted by water on the bottom of the tank, what I need to know? The formula, we have already derived it in the last class, right? The pressure is equal to H rho G. H rho G is the pressure, where H is the vertical height, rho is the density, and G is the acceleration due to gravity, right? Now in the case of water density, remember I showed you a table of the densities of various liquids and solids, and in that you would have remembered the density of water is 1000 kg per meter cube, right? So density of water is 1000 kg per meter cube. What is G? G is 9.81 meter per second square, right? That is also known. And what is H? H is the height. What is H here? It is 10 meters, right? So what is pressure? Pressure is equal to 10 into 1000 into 9.81, right? Which is going to be uh, 1000, 10,000, so 98100 Newton per meter square. No, 10 into 1000 into 9.81. So which is 10,000 9.81.
Oh, the 1000 kg there.
Yeah. 1000 kg per meter cube is a density. So I have substituted rho with 1000. At just 10, right? So the pressure exerted per meter squared of by the water of 10 meters is 981,000. You know how heavy is this?
Very heavy.
It's very heavy. Why? Because 98,100 Newton. If you look at 110,000, so this is going to be 9 tons weight. 9 tons per meter squared. 9-ton weight is acting. 10 meters of water. So it's very heavy, right? So 98,100 Newton per meter squared is a pressure. What is a force? Force is equal to, sorry. So what is a force? What is pressure? Pressure is equal to force by area, right? So pressure is equal to force by area. That is, force is going to be equal to, students, what is force going to be equal to?
Force is going to be equal to area into pressure.
Area into pressure. Absolutely right. Which basically means it will be 98,100 into what is the area?
Area 9 meters.
No, area is going to be
Length into breadth.
which will be
20.
20. Yes. So that is going to be 2611900 Newton. That's a force. So this tank should be constructed with real strong concrete so that it can withstand this force, right? So this is basically what the whole thing is. I just wanted to show do a problem and show you, right? Now, is there any questions on this? So we found a pressure, which is using HROG as a formula, and then you found a force, which is pressure into area. Pretty simple. Any questions? Okay, fine. So okay. Now, I want to just once again one more problem I want to do, right? Oops. So I have a tube like this. Oops, Control Z. I have a tube like this. Okay, and this tube has got water. Tube has got water inside. I want to know what is the pressure at this point. What is the pressure at this point? Okay, let me mark it with a different color. What is the pressure at this point, and what is the pressure at this point? Okay, now point A and point B. Now I'm going to give you dimensions. Okay, so dimensions are this. Oops. This is 20 centimeter. Okay, and this length is 10 centimeter, and this height is 15 centimeter. Right? Liquid is water. I want to know what's the pressure here and what's the pressure here. What is the pressure? What is the pressure at A and B? That's a question, right? Now, if I want to find the pressure at A, what should I know?
The length and breadth of it.
No, what length and breadth of it? If I want to know the liquid pressure at a point, what all things should I know? Pressure is going to be equal to, pressure is H rho G, where H is the
Where H is the vertical height.
vertical height. What is the vertical height at A?
15 centimeter.
No, vertical height it should be from where to where?
From
15 centimeters bottom to. Is that what you have to see? Is the pressure executed this way? When you are looking at the vertical column, should be the vertical column above or below the point?
above.
Above. So how much is that? How much is H? Vertical column above A. What is the vertical column above A?
Above 20 centimeter.
Absolutely. Why are you taking 20 centimeter? The reason is because if I know what is the pressure here, right, directly below this, it will be the same pressure here. Why? Because of, if I know the pressure here,
Yeah.
if I know the pressure at this point, which is the same level as A at this point, then the pressure here will be same as this. Why? Because of
Because of
what will be pressure at this point?
pressure at this point.
Pressure at this point.
H rho.
H rho G. What will be the H there?
The vertical height.
Which is
20 centimeter.
20 centimeter. Right? So I find the pressure here, assume, which is H rho G. The pressure here will be same as this. The reason is because the pressure is exerted in all directions in same equally. Pascal's law. Because of that, at this level, everywhere in the liquid, the pressure will be the same. That is why here the pressure is the same. You don't have directly above it, you don't have that liquid column, do we? No. But still the pressure is going to be as much as the 20 centimeter liquid column. Because the pressure executed here is equally exerted across the whole level in this liquid. So A also will have the same
Not
pressure.
the whole tube.
No, why? Because here it will be different. Here the vertical height is different.
So this tube.
So H here is
So the tube here.
Huh.
So there are. We can actually divide them into three different halves, and then in that first half and this, it this much will be till here. It may be having the same pressure. Here it will be same. Here also will be same.
no, here won't be the same. If I take a point here, what will be the pressure there?
Can't be the same.
It can't be. Why? Because the vertical height, it is not 20 centimeters. It's less than 20 centimeters. Right? Correct. But as I go down here, I am taking a point here which is at the same level as A. Then the pressure is 20 centimeter liquid column. So here also it will be the same. So the whole liquid column, same level, the pressure is the same. Because the vertical height is the net vertical height is what you see. Right? So you understood the point? Clear? See, what I was saying is,
yeah, I know, because they will have, both of them will have the same pressure, because the amount of pressure exerted is equally same around the
yeah. So see,
and the point you marked, it was at
so
a
if
level
I,
somewhere near A.
yeah. So if you look at this point here,
It is near A.
yeah, it is A, let us call it A dashed. It is at a depth of 20 centimeter and you have a liquid column directly above it. Now, so you have 20 into density of water into G as the pressure here. Right? Now, then the next point here also will be same pressure. Here also it will be same pressure.
Because
Here
they're
also
all in the
same level as A. Yes. So because of Pascal's law, equal distribution, equal amount of pressure will be there in all directions in that same level. That is why A also has the same pressure as A dashed, because A is at the same level as A
Now, what is
dashed.
the pressure of A?
Yeah, so that's what you're finding. So what is the pressure of A? It will be same as H dash. Yeah, so what is G? H? H is?
H is 20 centimeter.
Okay, so let us change the color here. H is 20 centimeter. Rho is? It is density of water, which is?
Mass by volume.
Yeah, what is the density of water? Last problem we saw, no? Density of water is 1000 kg per. What is the unit of volume? Think. Meter cube. Yes. So 1000 kg per meter cube. G is 9.81 Newton a meter per second square. Okay. So you know all these. So what's the pressure? Pressure is
force by area.
No, what is this? See to here, H rho G, right? Pressure is H rho G, right? What is H? 20 centimeter, which is in meter will be?
20,000.
No, centimeter to meter conversion, what should you do?
100 centimeter.
No, 20. So how do you convert centimeter to meter? So 20 centimeter will be? 20
20
by 100.
Which is 5 meters.
No, 20 by 100 is?
5?
How? It will be 1 by 5, right? How will it be 5? 20 by 100 is? In decimal it will be how much? 20 by 100 in decimal will be?
Can be cut, right?
Yeah, so these two can be cut, so it will be 2 by 10. So what will be? What will be in decimals? 2 by 10 is? In decimals will be? 2 by 10 in decimal will be? 0.2 into 1000 into 9.81, which is going to be 200 into 9.81, which is 1960 Newton per meter squared. 1960 Newton per meter squared is the pressure at A. Pressure at A. Now, see, I didn't even bother what is the diameter of this tube. Whether diameter is small 2 millimeter or whether it is 20 centimeter, doesn't matter. Diameter, only thing which matters is the vertical height of the liquid column. Anywhere. Only which matters is vertical height. Nothing else matters. Right? Now, what will be the pressure at B? So, this is pressure at A, PA. So, PA is 19. What is PB? PB is again H rho G. But what is H here? What is H here?
It is 20 centimeters.
No. At B, what is H? A, it is 20. No. See, this is a continuous liquid column. So the total vertical height above B, is how much? See, A already has this much pressure. See, here what is the pressure? PA, right? That's what you computed. The pressure at point A is what you have computed, which is 19620. So here the pressure is PA, correct? What will be PB? PA plus the pressure executed by this liquid column. Already this PA here. PB is PA because PA is exerted down. In all directions it's exerted. So it's also exerted down. Correct?
Yes.
Correct? So PA is exerting down. Now at PB it is PA plus this liquid column. That also get added. You understand?
I understand.
Clear?
Clear.
Sure.
Sure.
So at PA there is at the point A there is pressure PA, and at point B now it is PA plus the pressure executed by this 15 centimeter liquid column. So in fact what it means is PB is equal to PA plus H rho G because of this, right? So PA is how much? PA is so instead what instead what usually people do, they see the total vertical height. What is the total vertical height? 20 centimeter plus 15 centimeter. That's all what you have to do. Instead of I just try to explain why are you finding total vertical height, because it is pressure PA plus this. What is pressure PA? It is because of H rho G of this
Yes.
plus H rho G of this. So it is 20 into rho G plus 20 by 100 into rho G plus 15 by 100 into rho G. Right? This pressure is because of 20 into rho G is the pressure, H rho G. See, pressure at
So already the vertical height is written there.
yeah. So I just wanted to show you. So at point A, the pressure is 20 by 100 into rho G. And point B is pressure at point A plus 15 by 100 into rho G. This liquid column.
Okay.
So in fact that is nothing but 20 plus 15 by 100 into rho G. Correct? So at any point I have to just find the total vertical height of the liquid column. So total vertical height is 20 plus 15. That's all I have to do. So when I say H, find the total vertical height of liquid column above that point. So at this point the vertical height is 20. At this point is 20 plus 15. So it is 0.35 into 1000 into 9.82. Right? I want you to find it, calculate it yourself, right? So what I want to tell you is always find total vertical height of liquid above the point at which pressure has to be calculated. So here at this point the total vertical height is 20 centimeter, where at this point it is 15 plus 20. So always find the total vertical height of the liquid column above the point, and that's how you should find the pressure. So the H is always total vertical height of liquid column. It doesn't matter what is the shape of the vessel. You have to just find the total vertical height. So here the shape of the tube is peculiar, right? Like this, it comes like a 4. But still, what you are bothered about is total vertical. So if you look at this portion doesn't contribute at all to the total vertical height. Why? Because it's a horizontal pipe. So only the vertical, and that too vertical height is the only thing we have to consider. Assume that this was slanting like this. Even then, you have to only find the vertical height. You have to consider only the vertical height. So find the total vertical height which is perpendicular to that point. Vertical height means it is perpendicular to this point. Perpendicular. Okay. I hope you are clear. Any questions, students? Any questions which you are not clear? I'm ready to explain it again if you have any questions. You're fine? Sure? Okay, fine. Try it out yourself. If you still have any doubts, please submit your questions, and yes, and I will definitely help you. Oops. So using the derivation that we did in the last session, we in fact computed the pressure in a water tank. I also showed pressure in a pipe and with some bends and all that, and saw how we calculated. The key thing is always consider the total vertical height of liquid column above the point where the pressure needs to be computed. That is the main thing that you have to keep in mind. Please try out more problems. If you have any questions or doubts, let me know. Okay? All right. So now let us go back to consequences of air pressure. Consequences of liquid pressure. Right? So we saw that the liquid pressure, when it is exerted, it is directly proportional to the vertical height of the liquid column. It is directly proportional to the density of the liquid. And then of course there's a constant acceleration due to gravity. It doesn't change. It is same across the planet. 9.81 meter per second squared. And now why 9.81? Wait, we have to discuss about kinematics and Newton's law for deriving the exact formula, right? Exact value of 9.81. We will derive that, so you don't worry about it. Okay, we will be deriving that. So now, what are the consequences of this pressure? So see, the thing is, let us look at sea or ocean, right? Ocean has depths of meters and meters of water. Now, what happens when you start going down from the water surface? What do you think will happen? You are at the surface of the sea. You are swimming in sea. You are at the surface of the sea. Now you slowly start going down. You dive down into the sea.
When we go down further and further, we start getting a little suffocated.
What will happen?
If you stay underwater for a long time.
That is because you don't have oxygen. That is fine. But that's not what I'm asking. Talk like a physicist. What happens when you go down deeper and deeper in the water? You have got higher pressure, absolutely. The water pressure starts increasing. Your body starts getting squeezed, right? Your body, because the water will start pressing you because of the pressure, right? So that is why you look at this deep sea fishes. There are fishes deep down in the sea, and many fishes won't even have eyes. You know why? Because deep down the sea is dark. There's no sunlight reaching there. So what's the point in having eyes? Right? So they are adapted to live in those deep waters.
And when they come to the surface, they're adapted to such deep water surroundings that there will be normal blood pressure over there.
No. So what happens is that since they are very deep in the sea, the pressure of water is so high there, their blood pressure, the inside the body, is also very high. So that blood pressure can, that blood pressure can oppose the water pressure, and because the blood pressure is opposing, so it's like this, you know, inside. So if you look at the the fish, right? So let me draw a fish. Okay, so there's a fish, and inside this fish, the pressure, the blood pressure,
is as high as that.
yeah, will be as high as water pressure outside. Water pressure.
And when they rise up to the surface of the water, it starts reducing.
No, so what happens is, if you bring this fish out to the surface, it will simply burst. Because the pressure, the blood pressure is so high, and when it comes up, what happens? The water pressure starts reducing. So what happens? The blood pressure is so high that it will simply burst. It's like
Nothing will happen to us, right?
nothing will happen to us, but that fish will die. So fish can only survive in that depths. If by any chance if somebody brings that fish up into the surface, it will burst because its blood pressure will be so high, and the pressure outside,
It will be it will be very convenient for the fish for fishermen.
no. So I mean, the sense those fish, it's very difficult to catch those fishes. They are like so down that fishing is very difficult, right? So the thing is, what I'm saying is, this is an adaptation. So since the water pressure is very high in deep sea, blood in their body flows with very high pressure.
So when they have, so you said no, and the fishes when they stay in they stay very deep inside the water where there's a lot of where there's very high pressure, and their blood also has that much has a very high pressure which can stand that.
Yeah.
But after it comes up, their body will still have high pressure.
Yeah.
But the water pressure reduces.
Yes, precisely. They'll burst. Okay.
Just like
Just
that happens with humans also. When humans stay inside, go deep down the water,
yeah.
they immediately have to come up.
Yeah. So I will explain about humans. What has to happen if they want to go down,
They
right?
don't have that high pressure as the water.
Yes, absolutely. So, what in the case of humans, what has to happen is they have to put deep diving suits. This is actually a deep dive. See, this is a deep dive suit. So the human will be inside, so that the suit takes all the pressure. Because if you are going down in meters and meters into the deep sea, your body just can't take, your ribs will simply crack. It will break and you'll die because of the pressure. Because your body is built just to take the atmospheric pressure, and of course that also I'll explain how it takes that, because your blood pressure inside is equal to the atmospheric pressure. It is because of that the atmospheric pressure is not squeezing you. Your blood pressure inside, yeah, we are adapted to that. But when you start going down to sea, what happens? The pressure is atmospheric pressure plus the pressure of the liquid, right? Yeah, they add up, isn't it? See, look at this. So we have not looked at pressure in gases, but I'm just trying to explain. So oops, what happened? Oh, it's gone this way. So see, what happens is, say, assume that this is the sea, right? So this is the sea. At this point at the surface, what's the pressure?
It is atmospheric pressure.
Atmospheric pressure. What's the pressure here?
It is atmospheric pressure plus the water, the pressure down there.
Pressure down there. So assume this is H. It will be atmospheric pressure P. Let me call it PAT, atmospheric pressure, plus H rho G. Right? So we know our body is adapted to live in atmospheric pressure. But as soon as you start going down, you have atmospheric pressure plus the pressure of this liquid column acting on you. And if you start going down, pressure will be so high that your ribs will crack and you'll be crushed. You'll be crushed and you'll die. Right? So to avoid that, the scientists have invented this thing called the diving suit. Right? So when you put a diving suit like this, see, this is a diving suit. So
how much of a deep you go, you still not have that
yeah,
not be crushed.
because the diving suit takes all the pressure, so that your body is not the pressure is not applied on your body, but it is applied on the diving suit.
The suit takes all the high pressure.
And the diving suit is made of steel and all that, very strong
High
thing.
pressure cannot crush it.
And in this glass also is special glass.
If it does not have that pressure, it will also be crushed.
Correct. So this glass is also special glass which can take high pressure, right? And his whole suit is made of various things which can take high pressure, right? And you can see it's got robot. See, it's not hand, it's a robot which can be operated by hand inside the suit.
So we made it a robot.
Yeah, this is a robot. So what, and inside this, no, inside there will be controls for this robot. So what you using the hand, you can, which is inside the suit, you can control, and if you want to hold something and all, you can do that using this. See?
So, but there is someone inside that.
Yeah, of course. So this is empty right now, but somebody will get into that, right? So this is an example of the effect of liquid pressure and how the deep sea divers use these kind of diving suits so that it can take that high pressure. Got it? Okay. Then submarine hulls. You know what is submarines, right? So submarines are those ships which dives into the sea and it goes through the bottom of the sea or in the depths of the sea, right? Usually is used by Navy so that submarines can do. Nobody will see the submarine because it's down below, right? So if you look at submarines, even submarines have to be built to take that pressure, right? Because as they go deeper,
but if the submarine is not that strong, it
will again be crushed. It'll be crushed. Yes. Yeah. So well, I just want to show you the submarine. Oh yeah, a lot of pressure. See, this is a submarine hull. And you can see, see how thick the steel. That depends upon which depth it is, right? But you can see how thick the steel hull is basically the body, right? You see how thick the steel hull it has got, so that it's very strong and it can withstand that high pressure at deep sea. So again, another example where the engineers have to, and the scientists who design and build these submarines have to consider the water pressure that can take. And these submarines are built to go to certain depths. It's not supposed to go below that, right? Because if it goes below that, the pressure is more than what it is built for, and again it can crack and it can be destroyed. Yes, absolutely. So it's built for certain depths.
It can sink meters and meters down.
Yes. So based on the design, it is built for diving to certain depths of the sea, and it can dive up to that depth. Beyond that, it is dangerous. Okay. So that is another example of submarines and the effect of the liquid pressure. All H rho G, that is all what it is, right? What I explained about the liquid pressure, the H rho G. Right. So now let us HDG. Yeah, rho. Why I'm saying rho is because rho is the most common Greek letter which is used to represent density. So I won't, because most of the textbooks that if you're going to refer will say a rho, and you should know that is rho means density, right? So it's a Greek alphabet which is used for globally accepted to represent the density. Okay. Now let us go and also walls of a dam. Another example, right? So if you look at a dam, here it is. So if you look at a dam, right, you can see that the thickness of the dam. You know what dam is, right? Dam stops water from flowing and it collects the water so that then this water can be.
But if it is not strong enough, the water will pass through and it will break.
So you can see the thickness of the wall. Yes, you look at the thickness of the wall.
It is
Here it is thin, but here it is very thick. Why it is thick here? Because
the pressure is higher there.
higher there, because of the height of the column. Here the height is only this much, whereas here it is very high.
More and more big the how more big it
More
is,
deep it is,
more big it is.
more deep.
Yeah.
More deep the water is,
If the
more.
dam is big, it will go to a certain amount of distance
Yes.
below the sea.
Not sea. This is not sea.
I mean, so whatever.
River. Yeah, river or lake or whatever.
Then it will have to be thicker and thicker.
Yes, that's be thicker, and that's what you can see here. It is thin here, but it is thicker and thicker as it go down.
Atmospheric pressure up there.
Yeah, here it is only atmospheric pressure, absolutely. But here it is so atmospheric pressure plus the pressure of so much liquid column. So you can see that the dam is becoming thicker and thicker as it go deeper and deeper. Right? So
What happened to those fishes there?
now that they're just showing that those fishes will also be squeezed. Right? Just to
But
show.
still they can stand it.
Yeah, so that's just to show that there is higher pressure. Just to show that. That's it. See, I want to show you. I want to also explain this diagram. Right? Now, you have all these tubes in different shapes, but you can see that what can you say about pressure at A, B, C, D,
They are
and E?
all the same.
All the same. Why? Because the vertical height is equal.
Because the vertical height is equal and they are all on the same level.
Yeah, absolutely. Perfect, Sid. Perfect, student. You have understood the concept. Okay? So you can see that A, B, C, D, E, everywhere the pressure is going to be the same because the vertical height is equal everywhere. Vertical height is equal, and you have the Pascal's law, which basically says that vertical height is equal everywhere the pressure is the same at that level.
But here, if the pressure has to be same at every, if you have to, here the tubes are of different shapes. So if both of them are, if all of 5 of them are the same, then it will be easy to mark the levels, right?
I didn't understand that. What was it? If all the 5 are the
All the 5 have the same shape.
all this, yeah, absolutely. So the question is if all,
Easy to mark the levels.
yeah, so if all the tubes had the same shape, it would have been easy to mark the levels. Absolutely right. But the point here which I want to show in this diagram is it doesn't matter what is the shape, whatever it is. The only this here you can see there is a small diameter here, there is higher diameter here. All those doesn't matter. Vertical height. That's it. Here you can see it's conic. Yeah.
The thing below.
Here.
The thing below. That's what you are trying to say.
Now what I'm saying is you look at the shape here. Here there is a small diameter, there is a larger diameter, there's a small diameter.
The vertical height only.
That's it. Diameter doesn't matter. Here it's conical shape.
Vertical height here.
Here vertical height is something. This measure between these two, but perpendicular distance between these two lines is the vertical height. Right? So how do you find the vertical height? Very simple. Take this point. Oops, I have to use a different color, which I would use. So take this point, draw a perpendicular from this point
So, but still,
onto this point.
the vertical height will be the same.
Everywhere the vertical height is the same. Why? Because the perpendicular distance is the same. Correct? Right? Perpendicular.
And even the levels below
So
are
you,
the same.
yeah, so look at this. Here also vertical height is this. This is the vertical height.
But
Here the vertical height is this.
if the
Vertical height is this. Everywhere it's the same.
the level below, if it wasn't the same,
Uh.
then it would have not been this easy to mark, right?
You mean that if this was here and this was here? Is that what you're saying?
What?
What happened?
Yeah, I don't understand.
Oh, sorry. No, are you saying that if in this
No, wait.
uh,
If the points marked over here
uh,
were not
were different, yeah. Assume this was marked here and this was marked here and this was marked here and that was
not be exactly
then it will not be the same. Because why? If this was marked here, this is the vertical height, right? And if this was marked here, this is the vertical height. And here, if this was marked here, this is the vertical height. So the vertical heights are not the same in that case.
Yeah.
But here, all the points in the same level. So all of them have some vertical height. Vertical height is the perpendicular height,
okay.
right? So that's what it is. I hope you have clear now.
Yeah.
So I hope this is clear. If you have any questions, any doubts, please let me know. Once again, I want to quickly show you how to go to our website.
Yeah, even on the please allow me to define back to what you explained before.
Uh,
Can I?
yeah, sure.
You were telling the deep diving
Uh,
sea suits.
yes.
It is also built. It is also built.
Uh,
You can it can be somehow related with the submarine as well. It can that deep water sea suit. It also must be built in some way, which can go meters and meters deep,
yes, yes,
and can also stand at amount of high pressure.
yes.
It can be related with the submarine. If it goes even more below more than the pressure it can take.
Withstand, yes. Yeah, so the point which the student was making is even the diving suit is made to go only to certain level of depths.
That's the same principle.
Just same principle as submarine, and if the person dives beyond the level, then the diving suit won't be able to take the pressure, then it will crack or get crushed and the person inside will die. Absolutely right. I just wanted to show you the website navayugstudy.wordpress.com. This is the Navayug Study website. You can find all the content here, right? And you can find the class 7 content. Class 8 content is soon going to come, and please use the website, and there are ways where you can submit your questions. You can request for Google Plus sessions if you want face-to-face sessions to kind of find answer to any questions, where we can have video sessions where we can do that. Okay, fine. All right, let's go back to the presentation. I just want to quickly touch upon that, so to just know that this website exists. All right. So, so these are the consequences of pressure in liquids. What about gases? Do gases exert pressure? Yes, it does. The gases exerts pressure the same way the liquid pressures exert. The liquid exerts pressure.
Windmills in this?
Windmills is nothing to do with this. That's outside the discussion of pressure, right? So the shall we discuss that offline about windmills? Let's go ahead, right? So pressure in gases. So the pressure in gases is just like pressure in liquids, right? It is the same concept that in pressure in gases is again height into density into G. Why? Because you should understand, just like liquids, even gases have mass, right? So just because gases also matter, just like liquid, gases also matter, and the gas also has mass. So if you look at so I want to just explain what I meant here. Look at this. This diagram is kind of showing a column of air, right? Column of air. So it's a column of air above the surface. Yeah, so gas also is just like liquid. So if you look at when you're sitting here, there is a column of air above you for a few kilometers, as much as the atmosphere is absolutely perfect, right? The student was saying it is pulled by the gravitational force. Absolutely, that's the thing, right?
Solid objects,
yeah.
We throw them up, they're pulled down.
Yeah.
That
gas is also pulled down, so gas has weight because of that. Same. So same concept as liquid, right? Even liquid, what is happening? Liquid has a weight, and that weight is what is exerted as pressure.
So all three matters of state have weight.
Of course, because any matter has mass. Any matter has mass. Any matter has mass. Whether it is solid, whether it is liquid, whether it is gas. These are the three states of matter, right? Any matter has mass, and if it has got mass, it has got weight. Because anything which has got mass is going to be pulled by Earth. So it's got a gravitational force. So the same concept of pressure that we talked about in liquid applies to gas too. So in the case of gases also, pressure is h rho g, where h is the vertical height of the gas, rho is the density of the gas, and g is acceleration due to gravity. The same concept or same formula that we derived for liquid applies to gas, and gases also Pascal's law apply. So the pressure exerted is going to be equal in all directions. So all the concept that we talked about in the case of liquids also applies to the hydrostatic pressure applied by gases, right? So if you look at the atmosphere, extends for kilometers. You might have remembered we had.
Any matter can be pulled by the gravitational force.
Yes, any matter which has got mass will be pulled by the gravity, right? So if you look at the atmosphere spreads for kilometers, right? So you have toposphere, stratosphere, exosphere, that sphere, this sphere, a lot of spheres, right? You would have learned that in geography in 6th standard, I'm sure. So it extends for many kilometers, and this is kind of a calculation. What is the pressure exerted by atmosphere on 1 meter squared of ground, of surface of earth, is equal to 10 tons. 10 raised to 4 kilogram, 10 to the power of 4 kilogram force. That is, huh?
Wait, yeah,
10
10 tons.
tons, right? It is as if the 10 tons is as if 10 elephants are standing one above each other.
Means 10,000. 10,000
Yeah.
kg.
10,000 kg force is 10 tons. 10 tons is like 10 elephants one over the other. That much weight. Think that much weight is the kind of pressure exerted on your body. But do you know? No, that is why the body is built where the blood pressure inside the body is equal to that of atmospheric pressure. So when the atmospheric pressure is squeezing you in, the body is pushing you out because of the pressure inside the body.
For atmospheric pressure, there is
Yeah, so that is what the body is built, where the blood flowing to the body has got dissolved gases, which has got a pressure slightly higher than the atmospheric pressure. So what happens now is,
it is not same with the
yeah, we can say, yeah, approximately same. So what is happening when the atmospheric pressure is exerted on the body is pushing out with the same amount of pressure, so both neutralizes. So you are okay. You don't know, oh, there is atmospheric pressure. You are absolutely. But if some other creature is coming from a different planet whose blood pressure is, assume it lives in Mars, where the atmospheric pressure is very, very low, because the atmosphere is very thin around Mars. Very, very little atmosphere is there in Mars. Not like Earth. Earth is a beautiful, wonderful planet with big, huge, with a lot of oxygen and all that. Yeah, it's mere coincidence it happened. But Mars has got a very thin atmosphere, so atmospheric pressure is very low. So if we land in Mars, what will happen?
we cannot stay there.
We will burst.
Because
Our blood pressure is, our blood,
our blood pressure,
yeah,
it is
Equal-
the atmosphere is the atmosphere is designed in such a way
no, the blood pressure is such a way,
the blood pressure is in such a way that it is equal to the atmosphere
Press-
pressure on Earth.
Earth, yeah, and the atmospheric pressure in Mars is very low. Yeah, and atmospheric pressure in Mars is very low. So what will happen? Pling, you will burst.
You will not
So you have to put special type of, and there are also other problems.
go to any planet.
There is some other interesting things. Your blood will start boiling if you go to Mars. Now you'll ask, why? Sir is telling a lot of crazy things. Blood will start boiling in Mars. I will explain. Don't worry. Time will come and I will explain it. Right? So I will not get into that. I am so interested in physics. I keep on telling different things. But I am just telling you, if I go to Mars, my blood will start boiling. Okay? So
Something to do with the atmosphere there.
absolutely, it is to do with atmospheric pressure. I agree about that too. So here, let us come back to this, right? So the atmosphere, there is air above the surface of Earth, and the air is matter. Air has got mass, and because of that the earth will pull air down, and because of that the air has weight, and hence it does exert a force down, which is a gravitational force. And you can see how big that force is. It's a big force, right? It's a big force. Every meter squared, so which is then when you say it is 10,000 kilogram force, it is 100,000 Newton, right? 1 kilogram force is 10 Newton. So 100,000 Newton of force is applied every meter square. So in fact, that is the pressure which is applied per meter square of surface, and we are able to withstand it because the blood pressure,
is somewhere equal to the atmospheric pressure.
and so it is pushing it out, so it is neutralizing. The atmospheric pressure is exerting inward, whereas your pressure inside the body is exerting outward, and it is neutralizing, and so you are fine. Okay, so this is what is going on. A lot of interesting things. So see, science is trying to explain your existence on this beautiful planet. Okay, so I hope you understood about the atmospheric pressure and why there is atmospheric pressure, and the same concept of pressure of liquids, the same concept applies also to gases, and that is why both liquids and gases are together called in science fluids. The fluids means liquids and gases. Both are actually fluids. Why? Because they share so many properties. They share the pressure property, density property. So many things are exactly the same between liquid and gases.
Earth atmospheric pressure is designed in such a way that it's neither too thin, neither too thick.
Correct. Absolutely. Okay.
If it is too thick,
No, you are talking about density. I mean air's density.
no.
Thick and thin, there is no pressure cannot be explained in thick and thin. Pressure is high and low. Density, yeah, correct. So you have got a right density atmosphere. That is what the student is saying, right? So we have a right density atmosphere. We have a lot of things which has come together where the life is possible, and it is a mere coincidence. It is a rare thing. Life is a rare thing in this cosmos, right? So we are all lucky to be born on this planet. Okay, fine. So that is about atmospheric pressure. So what I told you is that the pressure in gases, pressure exerted by atmosphere is called atmospheric pressure, and we've seen that, you know, it is, yeah. So what is Pascal? Pascal, okay. So to go back to the units of pressure. So units of pressure. So what is the unit of pressure? So pressure is equal to force by area, and force unit is, in SI unit is, force unit is Newton, and area unit is meter squared. So Newton per meter squared is the unit of pressure, and Newton per meter squared can also be called Pascal. Why? PA. It is represented as Newton per meter squared is nothing but PA.
What is kPa for that?
So kilopascal, that is 1000 Newton per meter squared. It's like gram, kilogram, same thing. So 1000 Newton per meter squared is 1 kilopascal. Okay?
That is 1000 grams?
No, not grams. I'm saying kilo means 1000. Kilo means 1000, right? So here you are having 1000 Pascal is equal to 1 kilopascal.
1 kPa is equal to 1000 Newton.
Newton per meter squared is nothing but Pascal. So 1000 Pascal is equal to 1 kilopascal. Okay? So the Pascal, why we have named it Pascal is based on Pascal's law. Pascal's law is so important. It's a very important law in physics and chemistry. It is used so much, right, to find liquid pressure, gas pressure, and so on. So that is why the unit is named after Pascal. Just like why the force unit is named after Newton, because he only brought the concept of force, mass, acceleration, lot of things. So that is why it was named after Newton. And pressure the basics of pressure and hydrostatic pressure was brought by Pascal. So Newton per meter squared is also called Pascal. Okay, so that is about units of pressure. All right, clear? Okay, so 1000 kilopascal means 1000 into so 100 kilopascal means how many pascal? So 100 kilopascal means it's equal to 100 into 1000 pascals, right? Because 1 kilopascal is 1000 pascal. So it is, we are talking about 10 raised to 5 pascal, or 10 raised to 5 Newton per meter square. So that's the kind of pressure exerted by atmosphere. It's very high. It's very, very high, right? By atmosphere. The pressure exerted by atmosphere at sea level is 100 kilopascal. That's the pressure at sea level. So you are having from the sea all that kilometers of atmosphere which is there above it, that is exerting that much pressure. Okay, clear?
Yeah.
Now what happens is, as you climb a mountain, what happens to the atmospheric pressure?
It starts increasing.
No,
I mean decreasing.
it starts decreasing. Why? Because when you're climbing up the mountain, the amount of air above you is reducing because you're climbing up. So lesser amount. So it's like this, right? So this is your earth, right? This is your earth. You are here. Then assume the atmosphere is up to here. So this much column of air is above you. Now you start climbing up the mountain. When you're here,
You will get closer to that.
so only this much is there now. So the pressure is lesser here. So the atmospheric pressure starts reducing as and when you climb up the mountain. And so you understood?
You get closer to the atmosphere.
Not closer to the atmosphere, Sidhu. What do you mean by closer to the atmosphere?
I mean that layer, and then you get closer to that layer.
Yeah, so basically that's not the way to tell, right? In physics you say the amount of vertical height of the air column above you is reducing. Correct? See, here the vertical height is this much. As you climb up the mountain, the vertical height above you is reducing, and because of that your h rho g. So what is happening? Oops, sorry. So here it is h1 and here it is h2, and what is it? h2 is
H2
greater than,
it is greater than H1.
and so h2 rho g is greater than h1 rho g. So the pressure here will be lesser than here. So the vertical height of the same concept of liquid. The vertical height of the,
The less the vertical height becomes lesser, the more suffocated you feel.
why?
No,
Now the suffocation is nothing to do with pressure. Suffocation is because the oxygen content also reduces as you climb up the mountain. So when you climb up the mountain, the oxygen content,
so less the vertical height becomes, less the atmospheric pressure becomes.
less the atmospheric pressure. Now, because of this, there are some consequences. We'll actually discuss that, right? So, but I hope you understood. So, as you climb a mountain, the vertical height of the liquid, the atmospheric column above you, or the gas column above you, is reducing, and because of that, your atmospheric pressure starts reducing as and when you climb up a mountain, right? Clear?
Yes.
Okay, cool. Okay, so magnitude of atmospheric pressure is pretty high, very high, right? In fact, and as we go to higher altitude, atmospheric pressure reduces. Why? Because the vertical column of the gas above you,
Vertical height is less.
yes, is reducing, and so your atmospheric pressure reduces. Now, gases and liquids are called fluids. Both of them are together called fluids, right? Because both gases and liquids have same behavior.
So it's a mixture of gases.
No, not mixture. No, not like that. Both gases, so there is both these states of matter. Gases are also called fluids. Liquids are also called fluids. So both these states of matter are also called fluids in science.
Okay, fine.
Not a mixture, not necessarily a mixture. So what I'm saying is that see, both gases and liquids share the same properties of pressure, right? Both of them are H rho G, correct? Both of them accept Pascal's law. Gases also follow Pascal's law, liquids also follow Pascal's law. So since both of them follow the same laws of pressure, they are also called fluids. Gases are also fluids, liquids are also fluids. Okay. Similarity on pressure exerted by liquids and gases. So as I told you, the vertical, so both in liquids and gases, as and when the vertical height of the column increases, the pressure
decreases.
Student is not concentrating. Okay, students, I have to concentrate when the session is going on. So when the vertical height of liquid or gas increases, what happens to the pressure? It increases. When the density of the liquid increases, when the density is higher, what happens to the pressure?
It decreases.
Think and answer. When the density of the liquid increase, what happens to the pressure? Okay, fine. So when the vertical height of the liquid or gas increases, the pressure increases. When the density of the liquid or gas is higher, then also pressure increases, because both the pressure is H rho G. So the pressure is directly proportional to the vertical height, and pressure is directly proportional to the density. Okay. Then the other thing, the Pascal's law, the pressure is exerted equally in all directions. Right? The pressure is exerted equally in all directions. That is Pascal's law. So both these things which we saw in liquids also applies to gases. I hope that is clear. Any questions?
No.
Students? Okay. So pressure in gases is clear. I think we have also looked at atmospheric pressure. I want to show you some few illustrations. Now look at this gentleman, what he is doing. So he is trying to sip some juice from this glass. And how is he sipping? How is he sipping it? What is he doing? Through the straw he is sipping it. But how is the juice coming up through the straw into his mouth?
Because he's sucking that straw and the air is moving inward.
So what does sucking really mean? So let us see what happens to his mouth. Right? So inside his mouth, so this is his mouth, right? And this is his lips, and he has got his tongue, right? He's got his tongue, and here is a straw coming in like that, right? And this is a glass with the liquid, right? Now what he does while sucking is he tries to push out all, he makes the tongue up like that, and he pushes out all the air inside his mouth. When he sucks, right? When he sucks like this, when he sucks, what he is doing? He is somehow pushing out all the air in his mouth. And when he pushes out all the air in his mouth, what happens? The pressure here is far less than atmospheric pressure. There's no air there. You have created almost like a vacuum. There is no air. So what happens? The pressure here is very low. Pressure inside the mouth is very, this is a tongue, okay? Is very low. And what is the pressure here? What is the pressure here?
It is a little more.
What is that? What is that pressure? It's the atmospheric pressure, right?
Oh.
Right?
It is a little more higher than the pressure inside the mouth.
Yeah, maybe it's far higher, because here is almost a vacuum. You push out all the air. So the pressure is very low here. Whereas here the pressure is atmospheric pressure. And what is the pressure here? It is atmospheric pressure plus the pressure of this liquid column. So all this pressure will, since the pressure here is so low, will simply push the liquid inside. Look it up.
And if you push the straw even more inside?
Yeah, that, see, this pressure increase is nothing when compared to that. Atmospheric pressure is very high, 100 kilopascal. This will be very little, right? So really the effect is because of the atmospheric pressure. So it's the atmospheric pressure which is pushing it inside. So here the pressure is very low, where here is the atmospheric pressure. So the atmospheric pressure is far higher than the pressure here, and hence, so let us say this pressure is P dashed and this is PA, atmospheric pressure. PA, atmospheric pressure, is far higher than P dashed, right? And hence very high. So PA is very high than P dashed, and hence PA pushes the juice up the straw. This is how you are sucking in the liquid or the juice. So who is really doing the magic? Everybody thinks my mouth is doing the magic. My mouth is pushing it in. It is pulling it in. No, atmospheric pressure. If there's no atmosphere, you sit in, you go to moon and try this. No, not going to work, because the atmospheric pressure is very low in moon. Nothing is there. I mean, in the moon there are also other problems. Moon, there is no gravitational pull also. It is very low. Most probably what happened to the water in weightless?
It become
one ball because of no gravity. Such things will happen in moon. Okay, moon is a very dangerous place if you look at all this. But you see what the atmospheric pressure is doing for you. Without atmospheric pressure, you are in trouble. You cannot even suck your Pepsi from your can, or your Maaza from the bottle, or mango juice from your cup.
Fly and drink it.
Yeah, you will be in trouble. So see how atmospheric pressure is helping you. Okay. So interesting. You are explaining things. So I hope you understood that, right? The role of atmospheric pressure. So let us continue. So you can see that is how he is able to So let us look at another small experiment. Here what he has done is he has taken a straw. He has covered one end of the straw completely with a finger, and he is dipping that straw into this colored water. Okay, let us start from there. Now he is, yeah, okay, you're done. Now let us see what happens when he lifts. See the magic. Look at that liquid. It is still staying there. Why? Why is that liquid still staying there?
Because of the atmospheric pressure.
Why there is atmospheric pressure? See, what is happening is like this. You have, okay. So there was this cup. Sorry for my bad thing. Now he put the straw inside like that, and he put a finger here, right? So he put a finger here and completely covered. Now when he took it out, what did you see? You saw the liquid still here.
Yeah.
And you can try this at home yourself, right? Now why did this stay? Because now when he has closed this, is there atmospheric pressure acting?
No.
Here? No. Why? Because I have covered it with a finger. So there is no atmospheric pressure acting here.
If there was atmospheric pressure, it would have escaped the straw.
Yeah, and here, but there is atmospheric pressure, right? So now that atmospheric pressure,
Will the liquid fall out?
it will not fall off. Why? Because the atmospheric pressure is able to it is able to you know,
If you let go of
support. It is able to, atmospheric pressure is able to support that liquid weight.
But if you let go of it,
Now, as soon as you remove the finger from here,
they will dip off.
why? Because here also atmospheric pressure, here also atmospheric pressure. Both are same. Then the net. So let us see what is it, right? Let us look at the condition. So now what is happening? There is weight. There is weight of the liquid acting this way.
So that finger is obstructing the atmosphere.
Yeah. So now there is no atmospheric pressure acting here. So what is happening? The weight is being supported by the atmospheric pressure. Now, as soon as he removes the finger, what happens?
It'll flow off.
Why? Because there is atmospheric pressure here, so these two can cancel, but the weight of the liquid is there, no?
Yeah.
So there is so there is atmospheric pressure PA plus weight acting down. So this is PA into area or whatever, right? Plus weight of the liquid is acting down, and what is getting up? PA into A acting up. So net there is a force weight which is acting down, because of which it will fall down. So you understood that?
Yeah.
So when you are covering it with a finger, at that point the atmospheric pressure is not acting above, whereas atmospheric pressure is acting below, so it is able to support the weight of the liquid. But as soon as you remove the finger, the atmospheric pressure is acting on both sides, it neutralizes. Net weight of the liquid is there, which will basically acting down, and so the liquid falls down. So you can see that's what's going on here. So as soon as he removes a finger, see, as soon as he removes the finger, the whole liquid will.
Atmospheric pressure acted from both ends.
Both.
The weight of the thing, it acted on that.
And fell down. Before that, atmospheric pressure was only from below to up. So it. No.
After you left.
Yes. Understood the concept? So this is how I can explain. So, dear students, you can explain many things around you by applying the principles that you learn. Right? I am just showing you a few examples, but there are more things that you can see, right, around your world. Do do try to explain things around you using the principles that you learn. Okay. One more thing which I basically want to show you is the effect of here. I want to explain this experiment. So you have in fact got you've got a can. So this is some Pepsi can or something. So this is a can, right? What he's going to do is he's going to put that inside a vessel where that can gets heated up.
Then after that,
Yeah. Yeah, then he is going to dip that into very cold, ice cold water.
they will crush.
It gets crushed. Now, I want you to tell me why it is getting crushed, right?
Let's see.
Yeah. So, what it has got is that inside that can there is a little bit of water. Okay, there's a little bit of water. So there's a little bit of water. He is going to put that inside. As soon as he puts that inside, what will happen? The water inside the can will start vaporizing. Right?
It's just like that fish, this thing, no? When it has very high pressure, and then when you bring it, it bursts.
Yeah, that's good. Let's see. So he is putting it inside. He'll put inside the vessel. He'll start heating it. The water inside the can will start vaporizing. Now what happens is, shut the door. Now what happens is that, okay. Now see what's going on. Now they are taking the can out. It's heating, then all steam will be there inside the can after a while. right? They'll take it out, and you can see it gets crushed. Now you should also observe how they dipped it inside. Okay, they dipped it with the opening into the water.
With the
Opening into the water, right?
opening end of the water. I mean,
No, opening of the can is immersed in water.
that's for opening end of the can.
Yeah. So let us look at what happened now, right? So this was a can.
We saw this before.
Yeah, I'm trying to explain now using physics what is really going on. So this was a can. There's an opening here, right? There was a little water inside. There was a little water inside. Little, very little, not a lot, very little. Now they kept it inside a container, right, and heated it. So there was fire, right? Heated it. Now while heating, what happens? All these water inside, little water was there, vaporized, right? So water vaporized. All these water vaporized, became steam. Now, so there is pressure, the vapor with lot of pressure inside that can. Now what they did is, this is this vessel where there is water with ice, right? So ice cold water, right? Ice cold water. What they did is they dipped where this opening is inside. So they dipped it like that. As soon as they dipped, what happened is all the steam which was trapped inside the can immediately condensed.
And burst.
No, when it didn't burst, it condensed, and as soon as it condensed, what happens? A vacuum is created inside. See, all the pressure because of the steam suddenly vanishes, right? Because steam became water. When the steam suddenly became water, what happened? All the pressure inside the can suddenly reduced. Because there's no more steam. It became water droplets.
It reduced to such an extent.
So it reduced, and so a partial vacuum is created. Vacuum means as if there is nothing, right? So partial vacuum, or we can say a partial vacuum.
Immediately condensed and the
Yeah.
pressure actually fell down.
Pressure reduced. Pressure reduced,
It fell
reduced because of
condensing of water.
steam. Condensing of steam, right? And so pressure reduced because of condensing of steam. Because of condensing of steam. So now what happened is pressure Pi inside, and outside we have the Pa, atmospheric pressure, right? So, right, Pa, pressure, atmospheric pressure is acting from all directions. So Pa is far greater than Pi, and so
The partial vacuum.
the atmospheric pressure pressed it and it got crushed, right? So this is what's happening. So there was steam, yeah, there was steam here, right? And when they did this with the opening,
Pressure inside the can was very less.
no, so when they got it outside, it was pretty high because there was a lot of steam inside.
It was very high.
Ah.
After that, it became close.
When they
The atmospheric pressure outside is very high.
Yeah, as soon as they dipped that into the ice cold water, suddenly the steam condensed, and so the pressure inside the can drastically reduced, and so the pressure inside was far lower than atmospheric pressure, so the atmospheric pressure crushed it.
So before that, the can was having a pressure higher than the atmosphere.
No, almost same as atmospheric pressure because of the steam.
But after it became less, it became crushed.
Yes. Understood?
Yes.
Clear? Okay. Don't you think it's interesting?
Good. Magical.
Yeah.
You didn't take that L up.
That's okay. Alright, so that is about the other experiment which I want to show you. Now, I want to also show you how a hand pump works, right? So these are all the consequences of air pressure. So first thing I have already shown. The body is not crushed because the blood pressure inside is equal to your atmospheric pressure. So it's neutralizing, and so the body is safe. That's something which I explained before. Air pressure in lungs, ear, etc. same as atmospheric pressure, right? So just because of that, you're fine, you are able to take it. Now, what happens when you go to higher altitude? When you go to higher altitude, for some people, their nose starts bleeding. Why? Because the blood pressure inside him, as you go higher altitude, what happens to atmospheric pressure? Atmospheric pressure is
when you're when you have a
when you go to high.
when you are not in a higher altitude, your blood pressure will be same with the atmospheric pressure.
Yes.
But when you go there, the atmospheric pressure decreases.
Whereas the pressure
Whereas the pressure inside
is higher.
But the blood pressure is higher than atmospheric pressure.
So the outside. So what happens?
So it bursts.
Sometimes it bursts. Understood? So that is what's happening. Then, why does a fountain pen leak when you go to higher altitudes? Very interesting point, right? Why does it leak? Because
I think
see, this is a fountain pen.
go to higher altitudes, it's I think so.
See, this is a fountain pen.
It will have a pressure more than the.
No, so so what is happening is, see, there is ink inside the fountain pen. This is the ink, right? And yeah, and there is air trapped inside. This is air trapped inside. Now, when you're down the mountain, you are not climbing the mountain. This air will be at the atmospheric pressure there, right? So this is it. This is a pen, and inside there is ink, and then this is the air inside. So assume you have not climbed the mountain. So now your house is somewhere near a sea. So yeah, now this air pressure is equal to the pressure outside, right? So let us say that this is PA. Now what happens is you start climbing a mountain. Now when you climb mountain, assume you reach the peak of the mountain. There the pressure is PM, above the mountain. Now this PM will be greater than or less than PA? It
will be less than PA.
PA is less than PA. So what is happening? So the pressure here acting is PM. Pressure here is PA. This PA is more. It's pushing harder than PM. So it starts leaking. Interesting, right? Yes. So all these issues starts happening because of pressure. So another consequence of
physics.
Yes. Okay. So another principle, right? As we go, suction of juice from a cup we have already seen, right? Hand pump. I will explain hand pump, right? So how does a hand pump work? Have you seen hand pumps? Hand pumps are used for pumping up water. See, this is a hand pump. What you do is when you crank this, that is like this, when you push it up and down, what happens is water starts coming out of this pipe, right? That is how the hand pump works. How the hand pump works is again because of atmospheric pressure. What really happens is, let us look at this animation. So observe what happens when this is going up.
The water is being sucked.
Yeah, sucked. Why it is sucked? The water is sucked into this. Why it is sucked? Because now when it is moving up, there is vacuum created here. A very low pressure area is created here, and here the pressure is atmospheric pressure, and so atmospheric pressure pushes the water up into this chamber, right? And then when it comes down, what happens? This valve opens, and when you're pushing it down, the water comes up and it goes out of the pipe. See, now it is going up. See, now it is going up. This water is going up and this is going out. Now the water is being sucked into this chamber. Now when it is coming down, the water is going up and going out of the pipe. Understood?
So when it's coming down, the water is going.
Yeah. So two valves, actually in your textbook it explains step by step how each valve works. I want you to go through that and understand it. If you have any questions, let me know. But this animation really makes it very easy for you to understand how that works. If you want, you can go through the animation once again. Just rewind the video and see it again and again to look at the animation. Okay. All right, so that is about that. So we have looked at the consequences of air pressure. We looked at atmospheric pressure, and we saw that atmospheric pressure is because of the weight of the air column. We saw that the pressure exerted by the gases is just like pressure exerted by liquids. It is H rho g. Both are called fluids, and they are dependent on the vertical height of the gas column and density of the gas. Pascal's law still applies. We looked at all the various consequences.
We came to know about that Newton meter square had something had another name that was called Pascal.
Pascal, absolutely.
And after that, we came to know 100 gram Pascal is equal to 1 kilogram Pascal.
Absolutely. Now I want to show you Otto von Guericke's experiment. He is the first guy who proved that atmospheric pressure is really high. People never thought there is something called atmospheric pressure. What? I don't feel anything on my body. It looks to be okay. What atmospheric pressure are you talking about?
Because our blood pressure is
that nobody knew. So he proved. Otto von Guericke, he invented a pump using which the air can be pumped out of anything, right? So now this is the experiment that he did. Oops, sorry. So this is the experiment that he did. Otto von Guericke. See, he took two hemispheres.
So he is Otto von Guericke.
Yes, he took two hemisphere steel globe, right, with two hemispheres, and those. So it was like this, right? So two steel globes like that, which were fastened together using nuts and bolts, right? So they were fastened using nuts and bolts, right? And then he used a pump to pump out air. He invented a pump using which he can pump out all the air inside this. So now what happens? The pressure inside this becomes very low, right? So pressure becomes very low, correct?
Yeah.
So now, pressure inside is Pi, pressure outside is Pa, which is atmospheric pressure. Pa is far greater than Pi, right? And then what he did, students, look at this. So what he did now? Now he.
I think this one.
Correct. So now what he did is he tied up lot of horses. So here there are 10 horses. Here there are 10 horses, and tried to pull to. Then what he did after he pumped out this air from out, he just removed this fasteners. So what he did is he put the two hemispherical steel, steel containers. He attached them together, then used this pump to pump out all the air inside this. So now what happens is the pressure inside becomes far lower than the pressure outside. And then he removed all these fasteners and then asked these horses to pull. People thought the horses will simply be able to pull it out and it will become
Because of the atmospheric pressure.
Then they understood atmospheric pressure. The king got like zapped. What is this? 10 horses both sides, not able to pull it apart. Why? Because that.
What is the atmospheric pressure doing here?
So what has happened is he did this, and he used a pump which he designed to pump out all the air out of this. So what happened now? There is no air inside. So there's no pressure.
There's something which is pumping the air out of it.
Yeah, so that he found, he invented a pump. He invented an air pump. He attached that to this and pumped out all the air out of this sphere. Right? He pumped out all the air. He found a pump, equipment to do that. That is his invention, right? Then when he pumped out all the air, what happened? The pressure inside becomes very low. Pressure outside is atmospheric pressure. So atmospheric pressure will press it inside.
Inside is very low, but outside is very high.
Very high. So what will happen? Atmospheric pressure will press it inside. So when the horses are trying to pull, so what is horses trying to do? Horses are trying to pull it this way, right? This way and this way. But atmospheric pressure is pressing it inward, like that.
Okay.
Correct? So atmospheric pressure is pressing it inward. Horses are trying to pull it outward. But atmospheric pressure is 100 kilopascal. very high. 100 kilopascal is the pressure. It is very, very high, right? The 10 horses trying to pull both directions still couldn't pull it out.
10 horses on each side.
Still it couldn't pull it out because of the. So he proved that atmospheric pressure is very, very high. It is not that it isn't. It is not there. It is there.
What
He
if
proved it.
40 horses pulled?
I don't know. Maybe it may open up, right? Okay, so that is what the Otto von Guericke experiment. So I think with this we kind of discussed about consequence of liquid pressure. We looked at the pressure of gases and consequence of pressure of gases, and Otto von Guericke experiment, which proved how high atmospheric pressure is.
Pen leaks when you go into high.
Yeah, and all the consequences, absolutely. Okay, so I hope you enjoyed the session. Please go through your textbook and go through all these portions in the textbook. I in fact have covered the complete CBSE topic for force and pressure. Now next two sessions are going to be on the ICSE subject, ICSE portions, which is about kinetic theory of matter, and we'll explain how the gases and liquids exert pressure. What is happening inside? How is it exerting pressure? We'll actually learn that. We will also learn, the buoyancy. What does buoyant force? Archimedes principle. What does that mean? We'll actually also look at that. Lot of interesting things to come. I'm sure you're going to enjoy it. Meanwhile, revise. Next session, please come prepared after revising all these portions, because all these concepts we're going to continue using in the upcoming sessions on force and pressure. Till then, bye. Have a great time.